Okay, so last lecture we looked at socket programming, and this is stuck. So socket programmer sort of, as we saw earlier, was introduced as part of BSD, and that enabled developing and writing networked applications in the environment that was developed in. So there was a Unix environment, and the assumption was that you are dealing with an internet kind of network. So when we saw how sockets worked last time, when you opened up a socket, what did you need in both forms of sockets? We saw TCP sockets and UDP sockets here. IP address and port number. So we'll continue with that theme of what the IP address and the port number signifies. And so IP address and port number was required by the sockets to identify the remote entity or the remote process that it wanted to communicate with. So this is the name So in a typical network, what is the functionality of a name? What functionality does a name have to provide? And we'll see what functionality the name provides in the internet. So sockets were written where for a specific instance of a network, and people saw a particular form of protocol layering, particular form of naming that seemed to work. As things have evolved, people have thought about this problem a little bit more, and have started to identify the fundamental characteristics of different parts of the network. And so one limitation has come out of the internet naming structure. So to understand the limitation, first let's try and identify what does a name provide in a network. It has to provide two functionalities. What are the functionalities? First one is sort of obvious, that is identity. A name must identify the remote process or the remote node that you're trying to communicate with, right? That's necessary. You want to talk to node B. So node B for node A is the name of node B. It's uniquely identifying the remote process that you intend to communicate with in a network. What's the second functionality? That a name provides, or a naming structure provides. Yeah. Well, that uniqueness is part of the identity functionality. So once you know the identity of the remote node or the remote location that you want to talk to, what is the next step that
Location of
Location, exactly. So the second step is location, or the second functionality. Now, ideally, a naming system should decouple both of them. But in the internet naming structure as it evolved, this IP address plus the port defines both the identity of the remote process as well as location. The IP address indicates the final location of the node, and the routing mechanisms or the network layer will then tell you how to get to that location. But both of them are sort of tied into this naming structure. Now, why is this architecturally sort of a bad idea? Yeah. Yeah. So your identity and your location are tied to each other, so it prevents mobility. So So suppose you have a long-running process or job that is communicating with other processes. It's running on some, you're running it on your laptop. When you're in school and you've connected your laptop to the Columbia wireless network, you assigned a particular IP address. That process is still running on the same port, whatever was assigned by the operating system. So your name of that process is the IP address and port. Now when you go home and you connect to your ISP using DSL or cable modem or whatever, your IP address suddenly changes. The process that was running has not changed. The identity of the process has not changed. But your IP address has changed. So according to the naming convention, your name has changed. So that process now becomes a different process. Although it's still doing the same thing that I was doing earlier. But because the IP address changed, so on the network, its identity has changed because of the change of location. So that's why tying these two together, people consider that it's not a very good idea. And you see examples of this in other domains. So instant messaging. When you're doing instant messaging, your identity, which is your handle or your nickname, is separate from your location. Every time you log in to the IM network, your identity is retained, but your location changes, your IP address changes, and in developing these IM protocols, you're able to tie these two together. The IM protocols know now with a particular identity, there's a new location. Similarly, if you're on some P2P file sharing network, you dynamically join and you leave, your identity is retained according to the P2P naming structure. Right? Some P2P systems keep a track of how much you have uploaded, how much you have downloaded to sort of build your credit into the system. Now if you just change ISPs, your internet service providers, if your IP address changes, your identity is not going to change. You'll still retain your old credit base. So the point that I'm trying to make is, in the internet naming system, identity and location have been tied together, but when people are writing application layer protocols or applications which form a network of their own, so instant messaging network is a network which is running on top of the internet, but it's still a network of nodes where the nodes are these IAM clients, or a P2P network. In all of these new networks, effort has been made to decouple identity and location, principally because coupling them together prevents mobility. So when you're writing your application, when you're writing some distributed application and it's sort of operating in its own network, you have to think carefully of the naming structure that you use for your application. In fact, the first programming assignment will deal a little bit with this. Okay. So now, the default naming system on the internet, which is this IP address, the directory system that's used to translate human readable names into this IP address, which is the real name of a node on the network. This is handled by the DNS system, the domain name system. So the DNS system was developed in the early 80s. I think John Postel's name is not here. He was a large part of it. It was developed at the Information Sciences Institute at USC in LA. This is a brief history of references related to DNS, the RFCs where the original DNS specifications were published, further changes to DNS. There are more recent changes to DNS which have been approved by the IETF, which is DNSSEC, a secure version of DNS. DNS, as you can see, when it was developed on the old internet, which was a bunch of academics and engineers who trusted each other. So in the original design, no one really thought about bad behavior or untrusted behavior. In the modern internet, you have rogue users everywhere, so DNSSEC has been proposed to improve on the security aspects of DNS. So let's see what DNS looks like, how it handles the directory service on the internet. So again, these addresses, which are the names, are used to identify routes. So that's the second property of a name, which is identifying location, where this particular named entity is residing. And the first purpose, which is identifying a service, again that's part of the IP address in the internet. So you're trying to identify a process or a service by a name and a port number, which you identify with that service. So the DNS name service, which translates these human readable names in IP addresses, it uses a tree-like naming structure. On top of this directory is the root of this tree, which is handled by the root name service. The children of this at this root are the so-called top-level domains in this naming structure. So the top-level domains are domains like edu, org, com, or .us, .ch, .il, for different countries. And all the children of these top level domains define other subtrees which define different locations on the network. So to reach a particular node, you have to go down this tree and find a route to get to a particular node. So www.cs.columbia.edu. If a client at some remote location sends this query to a DNS server, the reply that it will get from that directory service is the IP address. And how this directory service is arranged is closely tied to how the naming system is arranged in this tree. So the first question is, can you implement DNS directory by a single database, a single lookup database, a centralized server where you send the query and you get the reply back? These are some simple calculations show you that it's not feasible to do it in a centralized single location. The number of queries can overwhelm any sort of server that you can build today. So issues involved are both the rate of request, how fast this directory changes, and how many replicas are needed to handle the total load. So because you cannot do it in a centralized way, you're going to distribute this load. And how are you going to distribute this load? You're going to distribute this load in a hierarchical manner. That's the principle that is followed by most of the architectures implemented on any network, because hierarchical distribution enables you to scale any sort of system. So the question asked here is, how does locality of resolution impact these considerations? So an example query and reply here is www.cs.columbia.edu. So that reply is given by a server. Now www.cs.columbia.edu is sort of the well-known name of the web server of the CS department. Where are clients more likely to generate queries for x.cs.columbia.edu or y.cs.columbia.edu? I'm sorry? More specifically? In cs.columbia.edu, right? So within cs.columbia.edu, most of your queries would be for machine names in the local network. So your queries here should be handled by a server that is close to you, so that the server responds fast, and it should be able to respond to all your queries in the distributed system. Now machines in our local network, they are not likely to generate a lot of queries for x.cs.stanford.edu. Right? A typical population of Columbia CS users do not want information about every network, every computer on the Stanford network. Maybe you want to go to the Stanford website, but you don't want to translate the name to IP address of every workstation on the Stanford network. So the queries that are being generated locally, largely they are of cs.columbia.edu, sometimes maybe for outside domain. So the distribution that is done, that's done in a manner so that the locality of resolution defines your architecture. So when you are distributing your database, the part of the database that's most important for a server is the part that'll get queried most often. So some of the issues involved with the name service design is that because you cannot do it centrally, you have to do it in a distributed manner. We'll see the architecture of how that is done. It has to be scalable. There are millions and millions of nodes. In the current internet, it's likely to become even more with IPv6. So it has to support not only a very large directory, which is the size of the database, but also a large number of queries to this directory. So it has to be scalable in 2 dimensions. Scalable in terms of the data that it has to handle, scalable also in the terms of the queries that it has to support. Multi-domain federation, well, we'll get to it what that means. And because it's distributed, this database, so both reads and writes to this database occur in a distributed manner. So that brings about another challenge of maintaining consistency across this distributed database. Yeah.
So where which server does it take? Where
We'll get to everything, all the details of how that's done. So performance again is related to scalability, and it defines the architecture. Then there's a question of security. We'll talk about that. And finally, extensibility. The basic DNS design was done to do a very simple host name to IP address translation. You can add more functionality to the DNS system and to any directory system that you design for any sort of network that you're working with. So the naming directory, names are these identifiers of resources or nodes, and the way these names are organized, it's hierarchical. So again, I said you have a top level domain. So in Columbia's case, our top level domain is edu. So all the children of edu are various universities in the US. Yeah.
Just to clarify one thing.
Yeah.
Not all of the edu TLPs are going to know Columbia.
I'm sorry?
Not all of the .edu TLPs will actually know Columbia. Some of them will not know about Columbia. Notice Columbia is not in every top level.
No, it's not.
So potentially when you run the query, you can come back to top level domains for edu that have no idea what Columbia.
But the top level server for edu will know where is the rights name server for Columbia.edu. So it won't have information about the entire Columbia domain.
So the top
But
level edu may not know the Columbia, but it will know who knows that.
who knows that? Yeah. So it'll refer you, it'll send you to the correct name server. So again, we'll get to those details. So below the top level domain of edu is the domain of the university, Columbia. So there are many different universities under this top level domain. Within Columbia, you have different departments. cs.columbia.edu, ier.columbia.edu, econ, all the departments that Columbia has and which have their own networks, they are in this level of this tree. Below this, you get down to individual nodes or individual machines. So what you are really trying to resolve is the name of a particular node at this level of the tree. So this tells you how the domain name server, the DNS system works. So the directory database is going to be distributed amongst all these name servers. At each level of the tree, there is a name server associated. And that name server knows either the complete subtree or at least who to ask in the subtree. So your resolver, which is, let's say, your web browser or your telnet client, is trying to convert this address, this host name, into an IP address. So the socket code might call get host by name or whatever. That will generate a query from this resolver to the local name server. Now this could be happening anywhere. It could be happening in Australia. So the local name server that's sitting in front of this machine, this default machine, will get this query, and as a first step, if it has no knowledge of this translation, it goes to the root name server and it'll ask the question, this is my query, resolve it for me. The root name server does not know the answer, but what it does know is the name server of Columbia.edu. So you went to the root top level server for the .edu domain. It did not know the answer, but it knew the location of the name server at this level of the tree. So it knew the location of the name server for Columbia.edu. So it will send its reply back, go ask Columbia.edu's name server, and this is the address. So the name server gets this information. Now it goes to Columbia.edu. Yeah.
The local server, what part of the address does it try to resolve? Does it try to see the left side, or does it try to see the whole thing, or does it try to start from the right side and read the whole address? Because suppose if you just, even local server just looks at edu and it has, or Columbia.edu and it has no knowledge, then it passes on to the root server. Or does it look at the whole string and says that I know this address and gives it back?
It looks at the whole string. If it has the address, it will reply. If not, then it goes from the last part of the address.
So in one way, you just have one layer of abstraction before the root server. So the root server is anyway going to have so much load. How much by how much factor have you reduced the load for the root server?
Because these replies are then cached.
Every time
these
radio comes, it knows where to send it.
Yeah, these replies are cached. Each record that is sent back has this field called TTL, time to live. So until that time to live expires, you're not going to go back to any server above Columbia.edu. You don't need to go there. You know the location of Columbia.edu. So again, when you send this when you send this query dcc.cs.columbia.edu to the name server of Columbia.edu, which is run by ASYS, it doesn't know the answer, but it knows which is the right name server for cs.columbia.edu. So the third query goes there and you get a reply and the resolver gets the right answer. So in this distributed database, all of these name servers are part of that database, and none of these name servers have the entire database, but all of them at least know where to go, who to ask if you want a particular information. So that protocol ensures that if there is a right answer, you will get it.
So
Yeah.
just one second. So once dcc.cs.columbia.edu is sent and gets cached, next time suppose it is abc.cs.columbia.edu, and this is the first step for a query for ABC. So when it looks up the entire thing, the local server, it doesn't know. Does it send it back to the root, or does it just send it to cs.kilometer radius?
So if it knows that the authoritative name server for cs.kilometer.edu is a particular machine, then it'll, and it's within the TTL, it'll send it to that one. So caching is done on all of these queries, and there are two types of queries on the DNS system. One is a recursive query, and the second is the iterative query. So in recursive query, you delegate the search to a name server, and the name server will give you the right answer. In iterative query, if the name server does not know the answer, it will give you where to go and look. So in this previous example, this is an example where the query from the resolver to the name server was a recursive query. The resolver wanted the final answer from the name server. The resolver did not want the name server to tell it, okay, you have to go and ask here. The name server provided the final answer here. So this name server was doing all the recursive queries on behalf of this resolver because the query was asked in a recursive manner. The queries that are going here are, on the other hand, iterative. You're not getting the final answer here, but this has given you the best help of where to go and look, and this goes on until you get the final answer. Yeah.
So the server in the tree is iterative and it can't cache the next level down, right? Like the name server, the root name server is iterative, will never cache.
Yeah, because it doesn't have the information. It'll never get the information. This root name server will never really deal with this particular address, but this one does. The next time you ask, it'll have the information.
But I mean, even like a really popular site like Amazon.com, I mean, the root won't know that either. We'll just know where to go to the com.
Yeah.
TLD, right?
Yeah. So again, caching helps in the performance of the system. It will store answers locally, so you don't have to go all over the place to get your answers. And the way this cache is managed is through this field called TTL, time to live for a particular response. The longer your TTL is, the better is the performance of the cache of the system, because once you get some piece of information, you don't have to go and refetch it for a long time. What is the downside of it? Well, when things change on the network, your directory will become inconsistent with reality. If within that TTL things have changed, that does not get reflected back in your cached result. If you have a very short TTL, then caching will not help, because every time you realize that the cached answer that you have has expired, so you will have to go out and get a fresh answer. So there's a trade-off. Of how to set this TTL, whether you want to emphasize performance or whether you want to emphasize consistency. Now this TTL field is also used very cleverly by CDN servers. So CDN stands for Content Delivery Networks. So companies like Akamai, they use the TTL field to do load balancing. We'll get to the details of that in the next lecture. First, let's just continue with DNS. So this again is explaining the process of resolving, let's say, www.cs.nyu.edu from a machine in the Columbia network, and how these queries are proceeding. So what kind of a query is this? It's recursive, because the local name server dns.cs.columbia.edu is getting the answer from the root name server. It's not getting the answer from dns.nyu.edu. It was not referred to some other name server. It asked the name server a question and it got the final answer. Iterated queries look like this. You are just referred to the next name server which is most likely to have the right answer. Okay. How are these distributed databases organized? Well, the whole namespace is partitioned into zones. Each zone is a subtree of this naming tree. So zones also allow a fair degree of autonomy in this distributed directory. So everything that's within a zone is controlled by some authority that resides in this zone. So we have a zone which is a subtree of Columbia.edu, which is cs.columbia.edu. Everything within that zone is controlled by a name server which resides within the zone. So if you add a machine to the network, if you remove a machine from the network, if you just change IP addresses of the network, all those changes are done locally here. It's under the authority of this zone. And there's a primary name server for a zone, and then there's a secondary name server for the zone. So these are authoritative name servers. They maintain authoritative zone databases for a particular subtree or for a particular zone. That doesn't mean that you're restricted to have only 2 name servers in a particular zone. These are authoritative name servers. You can run your own local name server, which will have its own cache and which will perform queries for you. Only it won't be authoritative. That a local name server will primarily act as a client in the whole system. It's acting as a server only for your machine. Rest of its functioning, it will just go and ask some authoritative name servers, either primary or secondary, to get answers. So you can have multiple name servers in a particular domain, but there are 2 authoritative name servers in a domain or a zone. There's a primary and a secondary. The root servers, there are 13 of them. And they always operate in the iterative mode or the iterated mode. They never operate in a recursive mode. These are the locations of the root name servers. Most of them are in North America. A couple of them are in Europe. One is in Asia. And I already explained what their functionality is, what service they provide. What is a resource record in this distributed database look like? So the elements that you are getting from this database, what do they look like? Well, there's an SOA record, which is the start of authority, which specifies what is the domain primary name server, what is the configuration of this name server. Configuration is who's the contact, the TTL for the reply that you're going to get, the refresh rate. Then there are other kinds of records. NS records specify the name server for a particular domain. So that will give you the authoritative name server for a particular domain. So here the NS records say that cs.columbia.edu, the name server is oak.cs.columbia.edu. Another type of record in this database is the address record, which is most often what we need or what we use. So it will translate or it will keep a name and address table. So here are the different names and here are the different IP addresses associated with that name. There is a canonical name record which specifies the canonical name of an alias. So if you have a machine oak.cs.columbia.edu, now oak.cs.columbia.edu is also the name server for cs.columbia.edu. Now suppose administrators on the internet follow this convention that your primary name server in a domain should be named ns.domain. Then this oak.cs.columbia.edu should also be identified by the name ns.cs.columbia.edu or yy.cs.columbia.edu. So this record will have this table which will translate all the aliases of this machine into this name. So aliases like yy.cs.columbia.edu or dns.cs.columbia.edu, which point to the same machine but are aliases of one machine. This CNAME record will translate the alias to the canonical name. A PTR record is the inverse mapping. So you just flip the address and the name. Host info specifies details of hosts like the operating system that's running, the CPU of the host and things like that. Well-known services specifies which protocols are running or are supported by hosts. Now clearly you can see that host info and WKS records, when they were designed for this very nice benign network where this database ran. Now you don't want to advertise what kind of machine you're running, what operating system you're running, what ports are open. Because if there are vulnerabilities, hackers will exploit that. So you want to make at least things harder for the hackers. So you want them to go and scan and try and find out. You don't want to advertise these things. So typically these records are left blank for machines. Host info, well-known service. Another record which is used is for mail support, and that's the MX record. So that's the mail exchanger record which forwards the email for any particular domain to a particular machine where the mail server is running. So when you're sending mail to joe@cs.columbia.edu, your mail program will then try and resolve, or again like DNS, it will send the mail somewhere else, and that server will then try and resolve where this message, which is destined for cs.columbia.edu, should actually go. Where is the mail server running? And this MX record tells you where is the mail server for a particular domain, and the mail is delivered to that particular machine which is running the mail server. The DNS query protocol again works in this request response mode. A client will dispatch query to a server. Server will respond with answers, and the transport protocol that is used, it's DNS allows you to use both UDP as well as TCP. A typical DNS query where you just want one address translation would fit in one packet. So for a typical DNS query, you don't want to go through the overhead of setting up a connection using TCP, having that virtual circuit going on, and then doing all your communications over that virtual connection, because in the end you're only going to exchange two packets. You send a query, you get a response. But there are situations where you're going to replicate a large portion of the database. So suppose you have a new secondary name server assigned for a domain. You're going to contact the primary name server and get details of every record for that domain which are held by that primary name server. So in that scenario, there's going to be a protracted exchange between the two name servers, which is going to be handled by DNS. And in that scenario, you want to use TCP. You want reliability. You don't want the overhead with every packet. But with a long connection, you want reliability, you want congestion control, and things like that. So there are different scenarios depending on the query where you can use UDP or TCP. DNS allows both. Protocol data unit. So what does the data unit of this DNS protocol look like? Well, it has different portions to the PDU. Every application layer protocol, or every protocol that we'll see in every layer will have what is called a PDU or a protocol data unit, and they'll have their own format. So the PDU format for DNS has the identification, which is the query source, flags associated with the query, whether it's a query or a response, whether the answer is authoritative or it's coming from some caching name server. If the answer is too long, then you set the truncated bit, which is telling you that one packet won't do. This exchange was happening over UDP, but you cannot fit the answer in UDP, so you should change the transfer protocol to TCP, or do something alternative. Then there's a flag which specifies whether this query is going to be recursive or iterative. Now again, this is a desired bit. Root name servers, even if you say that I want a recursive query, can simply refuse. So you're going with a request that, okay, I want a recursive query. Recursion available bit, the name servers, if they do serve as recursive queries, then they'll indicate with this bit that they do. Root name servers will unset this bit. The query format itself will have the query name, the sequence of names to be resolved, what kind of resource record is sought. So we saw earlier what kind of resource records there were. There were the address record, NS record, CNAME, MX, and the query class. So potentially DNS can work for all kinds of networks. For internet, query class is 1. And this is what the PDO actually looks like, where all those fields fit. This is what a typical packet would look like below the transport layer headers. So this is the application layer protocol data unit. So again, just to reiterate how it works, the application will invoke the resolver. It will ask a query. This resolver will send a recursive query to its local name server, and then the local name server goes through iterative queries, gets the correct answer, and supplies it to the resolver. There are some performance issues. Again, we spoke about that earlier. Your architecture has to ensure that fast performance is delivered to all the resolvers. So you replicate your name servers as much as possible so that the server load is light. Misconfigured DNS servers can cause failures. So if the database is not consistent with reality and the location of the remote node that you're trying to contact or trying to resolve has changed, then the DNS database will cause failures in these communications. DNS servers also become communications bottlenecks. Often people have measured that when you're doing web browsing, the maximum amount of time is spent resolving a host name than actually downloading a web page. Once you have the right hostname IP address, bandwidth is not the bottleneck anymore, at least if you have a broadband connection. The bottleneck becomes just doing this directory mapping. So sometimes when you observe that the web is behaving slowly, it may not be because the bandwidth from your machine to the internet is becoming congested or is becoming low. It could also be because the DNS servers which are involved in your query processing, they could be overloaded. So bandwidth is not always the bottleneck. DNS servers can become the bottleneck, and they do become the bottleneck often. So these address records, we already know that they are very important for any communication over the network. So it's important that we get the right resolution, the right translation between IP addresses and the host names, and it works in both ways. There is this protocol called rlogin, which lets you log in from trusted machines to a server. It won't ask you for your password. If you just send your login ID and your IP address, then this rlogin protocol lets you log in through trusted clients. So if someone can change the DNS server so that the name remains constant, but the IP address translation becomes different, then remote machines can log into this server. So if you're able to change this database so that the translations become different, then remote machines can break into your server. On the other extreme, servers can be compromised by what happens with DNS. So suppose you do online banking, and a web browser will translate homelink.fleet.com or whatever to an IP address. You're never really going to look at what the IP address is. That's all transparent to you. Now suppose someone compromises the DNS system and changes the IP address record for homelink.fleet.com temporarily. You open up your web browser, you try to log in, and you are redirected to this wrong IP address, which is running something which looks like your online banking homepage. You try to log in, there is some failure. But now this rogue server has captured your username and password, which it can use later when things get corrected. So security is a very important issue with DNS. This directory should not falsely identify either clients or servers. So every name resolution should be trusted. The other issue with the security is denial of service attack on root servers. This actually happened a few months ago, and it sort of slowed down the internet a great deal. Again, it slowed down because the root name servers were attacked. The bandwidth of any of the links did not go down, but the root name servers got attacked. The name resolutions took a long time, and so any communication over the internet got slowed down. So this directory service is very critical for the functioning of the network. It's also susceptible to this man-in-the-middle attack. A man-in-the-middle attack where you can have this rogue user who's sitting between your query and your DNS server. It can snoop, it can listen to your queries, and it can send back, it can intercept your queries, intercept the replies, and send back fake answers. So the architecture is susceptible to that, and that's why DNSSEC has been implemented, which addresses a lot of these things. Denial of service attacks, still, that's a separate issue. Additional notes, we already spoke about the limitation of the architecture, where it's not very amenable to mobile or dynamic computing environments, where your identity remains constant but your location changes. With this system, your identity and location are tied together, so there has to be a way to decouple that, and either you can hack DNS, add some kludges which will let you do that, or you can come up with a different naming system altogether. And application layer networks or environments, or what are called overlay networks, the P2P networks or instant messaging networks, come up with their own directory service to get around this mobility problem. Using DNS for load balancing, we'll see that in the next lecture, of how CDN, the content delivery networks, work, how they use DNS for load balancing, and how the TTL field is exploited. It's very clever what is done there. I spoke earlier about extending DNS, so generalizing resource discovery. So it goes beyond. Remember the resource records that we had with DNS. One record was mail exchanger, to specify a mail server. So we can extend DNS to provide more information or more specific information, this directory system. So find a print server which is within 1,000 feet of the querying node. So there are various proposals of extending the DNS to handle more generalized queries. So now let's quickly, okay, we'll start looking at signaling. So what is signaling and why is it important for networks? So network services, whenever you are doing this communication over a network, you're going to require state establishment at various nodes. And this state has to be consistent across these multiple nodes. So for example, if in a simple web browsing session, you're going to open up a TCP connection between the client and the server. So the state that is established at both the client and the server is the identity of this socket. The client IP address, the server IP address, the port numbers. This state is established at both ends. Another example would be if you're establishing a rail circuit over the network, then you need to reserve resources on all links in your path. So that resource reservation has to be done at let's say every router on the path. So signaling is the way you exchange these control messages to establish, maintain, or tear down network services. It's basically used to manage state in network nodes. So here is an example of a multicast scenario. So in a multicast scenario, one sender can transmit to multiple receivers at a time. Any receiver that wants to listen to this particular sender has to inform all the routers in the path that I want to listen to this sender. Any packet that is coming from this sender, forward it along. If you don't tell it to these routers, roughly, these routers will drop those packets. We'll see how multicast works, but since this packet is going to multiple receivers, this packet does not have a unique destination address. It is sort of going to some virtual multicast address which is not associated with a unique machine. So for routers to forward this packet along, they have to know that this packet is really required downstream. So to do that, every receiver will send a message across to these routers, and state is established at the receivers and at the routers saying that I want to listen to this sender, please forward packets along this path. So this is an example of these control messages being exchanged. So control message is exchanged between the receiver and the router, and the receiver and the sender. Sender also has to know that it has to send packets in this general direction. So this is another example of control messages and establishment of state. So the state that is established here is some sort of filters will be established at these routers, and the sender knows that they are active receivers, so it will continue sending packets. So some state will also be established here. So signaling is this exchange of control messages, and there are two very different approaches to do this signaling. One is called hard state and the other is soft state. So we'll look at how do the soft state and hard state approaches compare to each other, what are the characteristics, what is the difference, how do you measure the difference, can you measure it quantitatively, and which one is better. So how does soft state signaling work? So in this scenario, you have a sender and a receiver. So the sender is trying to establish state at the receiver. So in the previous example, the sender could be the receiver of the multicast transmission, and the receiver could be the first router on the way. This will explain how soft state signaling establishes state. So there's a signaling plane and then there's a communication plane. So this state, the sender wants to establish at the receiver. The signaling is done in a best effort manner. So what do I mean by best effort manner? Well, the sender will try, but it will not do it in a reliable manner. If this packet gets lost, then hard luck. The signaling is done best effort in the signaling plane. If it does get installed, then the sender sets a timer with this state. And this timer is also set at the receiver end. When this timer expires, in the soft state mechanism, the sender is going to resend this state across the network to the receiver. So every time the timer expires, the state is refreshed at the receiver. There is a state timeout timer, and if the receiver does not receive this refresh message, then after a timeout period, the receiver will remove the state. And in pure soft state signaling, that is the only way a state is removed. Once established, if you don't receive a refresh timer, then after a timeout interval, you're going to remove the state. Hard state signaling is different. So in hard state signaling, again, you're trying to accomplish the same task. You have a state at the sender which you're trying to install at the receiver. There is a signaling plane and a communication plane. This signaling is reliable. So when you send the state across, the receiver is going to acknowledge whether it received the state or not. If no acknowledgement comes, then the sender will try and send it again. So this is different from best effort. This is reliable signaling. Until the state gets installed, the sender will keep on trying to install the state. The state removal also happens by request. In soft state signaling, what happened was your state timed out if the refresh message was not received, and that's how the state was removed. Here, the sender will explicitly say, please remove the state. The receiver will receive that, it will acknowledge, and then the state is removed. So all that happens in the signaling plane, all the reliability. And in the communication plane, there are some errors that need to be handled. Errors in transmission, your network could get partitioned, all sorts of things could happen. Now hard state signaling is the approach which is used in telephone networks. Whereas on the internet, the approach that is used is soft state or some variation of soft state. So what is the basic problem in hard state? In hard state, it might be very difficult to recover from errors. So suppose your sender has installed a state and then the sender machine crashes. Because state removal is done only by request, that state will be maintained by the receiver, and that stale state will continue to exist. Yeah.
Does the receiver have a timeout eventually?
So you have to build in a timeout mechanism with hard state protocols. So in any network where there is a chance of error or failure, you have to build a timeout mechanism, otherwise you'll get into deadlocks. Another way to look at this is you can launch denial of service attacks. So a web server has a finite number of sockets, a finite number of ports or sockets according to the operating system. And if you use a hard state signaling approach, you can just create the TCP connection and never close it. And very soon the server will run out of sockets and it won't be able to serve any more requests. So this was actually done in the TCP SYN attacks, if you've heard of that. These rogue machines kept sending request establishment messages to servers. So servers used up their sockets trying to establish this connection. But the clients never followed through with the connection. They just locked up those resources and the server was rendered useless. Even though CPU resources are available at the server, bandwidth is available, because you made the server run out of sockets, you launched an effective DOS attack with very little utilization of resources on your part. So unless you have a timeout mechanism, your system is very susceptible. And then the question is, how do you choose the timer value? So the signaling spectrum looks something like this. You have pure soft state, and then you have pure hard state. In red, I've listed protocols which implement pure soft state and pure hard state. The characteristics of these signaling mechanisms. In between, there are variations of soft state. So there is soft state plus explicit removal. So in that scenario, soft state protocols also send an explicit removal signal, which the receiver receives, and then it can remove a state. So timeout is not the only way to remove state in soft state plus explicit removal. So internet protocols like IGMP use soft state plus explicit removal. There is something called soft state plus reliable trigger. So in reliable trigger, what you do is your signaling in soft state is also reliable. It's not best effort. So you send a message, then you wait for the acknowledgement to come back. So your signaling becomes reliable. There is soft state plus reliable trigger and removal. So again, you build sort of more characteristics of hard state into the soft state protocol. The next lecture will continue with this discussion, and then look at web caching, CDNs, and maybe the HTTP protocol.